A process plant is made up of many systems and many different types of equipment. All of the systems and equipment work together to produce a product. The operation of plant systems and equipment is based on scientific principles. Understanding these principles will give you a better idea of what's going on in the plant. For example, if you understand the principles of heat transfer that enable a heat exchanger to heat or cool fluids, you will be better able to determine whether a particular heat exchanger is operating properly. And if you understand the principles of fluid dynamics, you'll know that when the flow rate in a system changes, the pressure in the system also changes. Some of the physical properties that we measure are referred to as dimensions. The fundamental dimensions are length, time, and mass. These three dimensions and the units associated with them are the basis for many of the measurements that are made in a plant. Two standard unit systems that are commonly used to measure the fundamental dimensions are the English system and the metric system. We'll use the English system for this discussion. The standard unit of length in the English system is the foot. All other measurements of length in this system, such as inches, yards, and miles, are based on the foot. Length is a basic measurement that is used to derive several other measurements, such as area and volume. Area is a measure of a two-dimensional surface, and volume is a measure of a three-dimensional object or space. Let's use this brick to see how length measurements are used to calculate area and volume. For our discussion of area, we'll focus on this surface. This length measurement is 2 inches, and this one is 4 inches. The area is calculated by multiplying these two measurements together. So 2 times 4 is 8. Since area is a two-dimensional surface, it is expressed in square units. For this example, since both sides were measured in inches, the area measurement is expressed in square inches. Other units of area, such as square feet, square yards, and square miles, would be calculated the same way. The volume of a rectangular solid, like this brick, can be calculated by multiplying 3 length measurements together. As we just saw, this surface is 2 inches by 4 inches. The third measurement is 8 inches. So 2 times 4 times 8 equals 64. Since volume is a three-dimensional measurement, it's usually expressed in cubic units. In this case, cubic inches. Cubic feet and cubic yards are also common units of volume and are calculated the same way. The volume of this object can be calculated by multiplying 4 feet times 5 feet times 12 feet, for a total of 240. Since the 3 length measurements are all in units of feet, the volume is expressed in cubic feet. Now, using length measurements to calculate the volume of a solid is not the only way volume is expressed. Volume is also used in measurements of fluids. The standard unit of fluid volume measurement is the gallon. A gallon is not a measurement based on length, but both cubic feet and gallons are used to measure volume. 1 cubic foot does not equal 1 gallon. This 1 cubic foot container actually holds 7.48 gallons of water. If we empty these gallon jugs into the cubic foot container, it should take just about 7.5 jugs. And that's about what it takes. This is not the only example of a situation where more than one unit can be used to measure the same thing. For this reason, conversion tables, or standard equivalence tables, are available to help you find measurements and their equivalents in other units. Although the second and the minute are 2 units of time that you're most familiar with, Flow rate and velocity are both derived from units of time. Flow rate can be measured in units derived from a combination of a unit of volume and a unit of time. Flow rates are used to measure the amount of fluid passing a particular point over a period of time. A typical unit of flow rate is gallons per minute, or GPM. For instance, this flow meter is indicating approximately 2.2 GPM. In other words, there are 2.2 gallons of water passing this point in the system every minute. Velocity is a measurement that is derived from a unit of length and a unit of time. Velocity is the distance traveled over a period of time, and it is often measured in feet per second. The third fundamental dimension is mass. Mass can be defined as the amount of matter an object possesses. But mass is not measured directly. The most common method of measuring the mass of an object is by weighing it. The standard unit of weight in the English system is the pound. The weight of an object is the result of the force of gravity acting on the mass of the object. Like weight, mass can be measured in pounds. On Earth, an object that has 1 pound of mass weighs 1 pound. As you may know, most of the measurements taken in a plant are related to process variables. The most common process variables measured are pressure, temperature, flow, and level. Let's discuss the units related to measuring process variables, beginning with pressure. Pressure is defined as force applied over a unit area. It's measured in units of force divided by units of area. Pressure is usually measured in PSI, pounds per square inch. To illustrate this, let's say we have 10 pounds of pressure applied over a 1 square inch area. We have 10 pounds per square inch. 10 pounds of pressure divided by 2 square inches is 5 pounds per square inch. In a plant, pressure is often indicated on a gauge, like this one. This gauge is indicating about 156 psi. In other words, the pressure at this point in the system is about 156 pounds per square inch. Temperature is another important process variable. Temperature is an indication of the relative hotness or coldness of a substance. The most common unit of temperature in the English system is degrees Fahrenheit. Like pressure, temperature is often measured at various points in a system. For example, this temperature gauge is indicating that the temperature at this point in the system is 232 degrees Fahrenheit. Flow rate is another process variable that is measured in plant systems. Flow rate is defined as the amount of fluid that passes a particular point in a system in a certain unit of time. Generally, flow rates can be measured in mass flow units or in volume flow units. This recorder indication is an example of one common mass flow unit, pounds per hour. On the other hand, volume flow rates are typically measured in gallons per minute or cubic feet per second. The last process variable we'll discuss is level. Level can be defined as the position of a surface above or below a fixed reference point. For instance, in this illustration, if the reference point is at the bottom of the tank, measurements are taken from the bottom to the surface, indicating how much of the tank is filled. If the reference point is at the top of the tank, measurements are taken from the top to the surface, indicating how much of the tank remains to be filled. Another way the level in this tank can be expressed is as a percent of maximum height. For example, the level in this tank is at the halfway mark, so we can say that the level is 50% of maximum height. Level is usually measured in units of length. For example, the scale on this tank is indicating the level in feet and inches. In this topic, we looked at the fundamental dimensions of length, time, and mass, and we identified some units that can be used to measure these dimensions. We also saw that many other measurements can be derived from these fundamental dimensions. We also saw that some measurements can be expressed in several different ways. For example, we saw how a volume measurement can be expressed in gallons or in cubic feet. Conversion tables help us express measurements in different units. Since most of the measurements that are made in a plant are related to process variables, we discussed the 4 process variables that are most commonly measured: pressure, temperature, flow, and level. And we identified the units of measurement that are generally used to measure these process variables. Now take time and try some practice questions. Length is a basic measurement that is used to derive several other measurements, such as area and volume. This recorder indication is an example of one common mass flow unit, pounds per hour. On the other hand, volume flow rates are typically measured in gallons per minute or cubic feet per second. Let's begin our discussion of force and motion by defining a few terms. Force can be defined as a push or pull on an object. For example, weight is the result of gravitational force which pulls all objects toward the center of the earth. Like gravity, all forces are invisible. For example, if we sprinkle iron filings on a piece of cardboard and move a magnet underneath the cardboard, the filings move because of magnetic force. But we can't actually see the force. In this case, what we can see is the action that results from the force. This resulting action is called motion. Motion can be defined as a body changing position. Applied forces can have several effects on motion, including starting a motion, changing the direction of a motion, or stopping a motion. For example, many process systems operate with fluid flowing through them. The flow in these systems does not simply start and stop. Instead, forces are often applied by pumps to start the flow, and forces are applied by valves to regulate the flow. So you can see why force and motion are important considerations in the operation of a process plant. Let's take a look at 3 basic laws of force and motion. Going over them can help you see how force and motion are related. The first law states that when an object is not moving, it won't start moving unless a force is applied to it to overcome its inertia. Inertia is a property of matter that resists changes in motion. An object that's not moving remains at rest because of its inertia. And when an object is moving, its inertia causes it to continue moving in a straight line unless a force is applied to it. Inertia relates directly to the mass of an object. So the greater the mass of an object, the greater the inertia. And the greater the inertia, the greater the force required to start an object moving, stop a moving object, or change a moving object's direction. Now, the second law deals with the applied force. Simply stated, the second law says that force, F, equals mass, m, times acceleration, a. Acceleration can be defined as the rate of change in velocity over a given unit of time. A change in velocity may cause an object to either speed up or slow down. So basically, acceleration is a measure of how fast an object changes speed. That is, either speeding up or slowing down. For example, as a result of an applied force, this ball accelerates from 0 velocity to its peak velocity. To understand this better, let's look at the action again, but this time we'll use a scale to show distance and a clock to show time. If the ball moves 2 feet in the first second, 4 feet in the second, and 6 feet in the third, it travels an additional 2 feet for every second that passes. In other words, it accelerates at a rate of 2 feet per second per second. Feet per second, or simply feet per second squared, is a common unit of acceleration. Just about anywhere there's motion, the relationship of force, mass, and acceleration is applied. In the flow of fluid, in the movement of solids, or in a moving vehicle. A good example of the first two laws at work in the plant can be seen in a pump startup. Here's a cutaway illustration of a centrifugal pump. We'll slow down the action so that we can explain what's happening. Before the pump is started, the fluid in the system is at rest, and its inertia tends to keep it there. The fluid has a velocity of 0. When force is applied by the pump, the fluid starts moving. The applied force causes the fluid to accelerate from 0 velocity to its final velocity. Once the fluid reaches its final velocity, the applied force and the fluid's inertia will keep it moving at a relatively constant speed. In this case, although the fluid starts at rest with 0 velocity, applying a greater force causes its acceleration to be greater and its final velocity to be greater. The third law of force and motion we'll look at states that for every action, there is an equal and opposite reaction. In other words, if a force is applied to an object, the object applies a force that's equal, but exactly opposite in direction. This law is usually referred to as the action-reaction law. The force that lifts and moves a rocket into space is the reaction force that results from rapidly moving gases that are created by the combustion of fuel. In the plant, an example of the third law can be seen in this demonstration using a compressed air hose. The movement of the hose is caused by a reaction force that's produced when air flows rapidly out of the hose. Another example is the pipe supports that keep pipes from moving when the fluid flowing through them makes a turn. As the fluid makes the turn, the pipe exerts a force on the fluid, and the fluid exerts a reaction force on the pipe, causing it to try to move in the opposite direction. So the three laws give us a means of analyzing forces and motions. In this topic, we looked at force and motion. We saw how force and motion are related, and we discussed three laws of force and motion. Nearly every aspect of plant operation is affected by force and motion, so it's important for you to have an understanding of the concepts that we covered. Now try some practice questions. Force, like the force that pushes this ball, can be defined as a push or pull on an object. Because of the applied force, the ball is in motion. Motion can be defined as a body changing position. Gravity is a force that acts on all objects on Earth. Gravity exerts a downward force or pull toward the center of the Earth. Now, the second law deals with the applied force. Simply stated, the second law says that force, F, equals mass, m, times acceleration, a. This ball is in motion because a force was applied to it. What would happen if a greater force were applied in the same way? What force causes these boxes to fall to the ground?